We're going to go through linear models today, and at the very end, remind me, we'll recap with rate of change so that we can kind of go over what we did yesterday. Here we have a set of data. With this data, we need to figure out if it is a linear model and if it's not. So today we're just focusing on whether things are linear or not linear. So first thing we need to do is figure out which is the independent variable and which is the dependent. We're comparing hours in pay. So somebody's at a job, and they're obviously getting paid. What would be our independent? Hours, right? So independent goes on which axis?
Y.
Goes on the x-axis. Pay being our dependent, right? Depends on how many hours we work. That's what's going to influence our pay. That goes on the y-axis. So this is our dependent variable. Actually, I got to move that. Oh, nuts. Now, if we have all of the data, does anyone know a way from just looking at the data without graphing it that we can tell whether something is linear or not linear? Yeah, increasing by the same amount, which Martino said, first differences. So what we're going to do for first differences, which is similar to what we had done from rates of change, we're going to take our y values and we're going to subtract them. Now we have to make sure the x values are going up by the same increment, okay? And in this case, everything's increasing by 1, so that works. If they weren't going up by the same, we couldn't technically use this. So we have to check that every time, okay? So because they are, we can now use our first differences. And first differences, we're going to start at the bottom. We're going to take the first number and subtract it from the one above, okay? So in this case, we take 84 and subtract 72. What do we get? 12. Excellent. Okay. And we're going to continue this pattern. 72 subtract 60. Yep. 60 subtract 48. 12. Good. 48 subtract 36. So what are we noticing as we go through this? Yeah, they're all increasing by 12. So what does that mean in terms of this relationship? It's linear, that's right. So because the first differences are all the same, it is linear. What if I'd gone through this, and this was 12, then maybe 10, 8, then 15, 11. Yeah, non-linear. We're not giving it any other definition today other than it's just not linear. So we're strictly focused on things being linear. Now when we graph things that are linear, what type of graph do we get? Yeah, we're going to end up with a straight line. We're going to verify that by putting this in. So we'll quickly look at our x-axis. It's going up by 1s. So on our x-axis here, which is going to be hours, okay? So our hours, we're going up by 1. So we'll see if this works. We'll go over by 1. 0, 1, 2, 3, 4, 6, 7. Perfect. That worked out. We have 7 units to go by. In terms of our y, which is going to be our pay, what do you think would be a good increment to go up by? 12? Yeah, we could go by 12, but let's do something that might be easier to count by. What would be very easy to count by? 10s. 10s are really easy. I don't think one will fit all the way from 0 to 84, right? So we go 10, 20, 30, 40, 50, 60, 70, 80, 90. Good. 90 encompasses the last number. So always try to make our graphs quickly and easy to count if we can. So this one's going to go 10, 20, 30, 80, and we technically have to get all the way up to 90. Good. So let's plot our points. The very first one being 0, 0, which is right at the origin. Second one is 1, 12. So we'll estimate 12, probably about there. 2 and 24. 3 and 36. 4 and 48. 5 and 60. 6 and 72. And 7 and 84, probably about there. And what we notice is we get a straight line. So it's definitely linear. This is 2 different ways we can determine. One is by taking the first differences. The other one is by looking at the graph. If we have a straight line, we know this is linear. And I'm going to give you the equation of this. It just so happens the equation of this is y is equal to 12x plus 0. Okay? This is a linear relationship. So if we were to look at it as an equation, what in this equation tells me that it's linear? Does anyone know? Actually, the plus 0 is the y-intercept. It's usually known as y equals mx plus b. Do you guys recall this at all? Yeah. B is the y-intercept. So the y-intercept, where it crossed the y-axis, was the value of 0. Okay? There is an exponent. What is the exponent? 1. So you guys remember we went through exponents. If we have an exponent on the variable of 1, that means we have a linear relationship. Only 1. What if I had written it as x squared? It's not. Anyone remember what that is? Yeah, parabola or quadratic, right? So, any other number, what if I had x to the negative 1? Anyone know? Is that linear? It's not positive 1. The goal is only positive 1. In fact, if it is x to the negative 1, that means it's 1 over x, and that gives us something that looks like this, which we don't talk about in this class. Okay? It has to be positive 1. Okay. So, the other thing I want you guys to notice is when we went through the first differences, we got a value. What was the value? 12. What is that in terms of our equation? Anyone know? What does the m stand for? Slope. Yeah, the slope of this happens to be 12 in this case. Okay? So, and the way we can prove that, tactically we find rate of change for slope. So if you guys remember, rate of change is our rise over our run. Okay? So we'll calculate that down here. Rise over run. Rise deals with which axis? The x or the y? Anyone know? Y, eh? So it's our change in y over our change in x. That triangle stands for the word change. Okay? So change in y divided by change in x. And if you recall from our formula, that was y2 subtract y1 over x2 subtract x1, which is also known as our slope. Look at how many different things are equal here. Rise over run is equal to the change in y over x, which is equal to y2 minus y1 over x2 minus x1, which is equal to slope. Tons and tons of different ways for us to remember this. Now, rise over run. What was our run in this case? 1. And that's exactly the difference between a pair of these. So I'm going to use the last two. Okay? I'm going to call this my x1. I'll use a different color here. x1, y1, x2, y2. Okay, so we'll write these coordinates out so I can remember. The x1 was 6 and 72. And so this was x1, y1. And the other one was 7 and 84, which was our x2 and y2. Okay? So we're going to plug these values into this equation here. Our slope, or our rise or run, or I should have written rate of change. So our rate of change, I'm going to call it ROC, rate of change, is equal to y2. Which one is y2? What's the value? 84. So 84, subtract y1, which is 72, divided by, what is our x2? 7 minus 6. And we said the run was what value? 1. 7 minus 6 is 1. And what was our rise? Yeah, remember it was 12 when we subtracted here. And 84 subtract 72 is 12. In other words, 12 divided by 1 is 12. This is our slope. It's also the rate of change. All of these things are equal with a linear equation.